Okay, we're almost all unmuted. We're all back. Awesome. Okay, hi everyone, and welcome to this week's Learning Space. I am your postdoc with postdoc Nicole Gugliucci with CosmoQuest. I am joined by my very awesome co-host down at the end of the screen.
At the end,
Georgia Bracey. Those of you who have been watching, we are still in the middle of our office move.
Boxes.
The boxes in the background, and Georgia's been kicked out of her own office. So, but we're still here. We're still going. So thanks for joining us. Feel free to share the link, to comment on YouTube, on the event page, or using the Q&A app for Hangouts. And we will be watching for your questions and comments, so say hello, ask questions, all the usual stuff. And I am joined today by James Madsen and Megan Madsen, both of whom work with IceCUBE, which is a searching for cosmic neutrinos from the Antarctic. And we asked them to come on to talk some about IceCUBE and the neutrinos, but also a lot about the education and outreach programs that go along with this project. And I'm really excited. I know very, very little particle astrophysics beyond what I learned in my high-energy astrophysics class in grad school, so I'm really excited to learn some new stuff. So thank you both for joining us.
Thank you. Yeah, we're looking forward to it.
Awesome. So, Jim, do you want to maybe start us off, just broad overview of IceCUBE for any of our listeners who haven't heard of it or aren't up on their neutrino astrophysics?
Sure. Yeah. It's hard to believe that there still are a few people that are unaware, right? Yeah. So, what we're really trying to do is develop a new way to study the universe, and so kind of the analogy I like to use is to look at medical imaging, right? And so 100 years ago, if you went into the doctor's office and you said you had a headache, they could look and see if you had a bump on your head, and that was about the extent of what they could do for you. And actually, probably 100 years ago, they did have the start of X-rays. So then you could look and see, do you have a skull fracture? But if you had anything internal, there wasn't much that could be done until we developed, MRIs, and actually were able to see soft tissue. And so taking more and more X-rays would never allow you to determine that you had a tumor, for example. So what we're trying to do is detect these particles from outer space called neutrinos in order to get a new view of the universe. And so the exciting thing is that we think we found the first evidence for neutrinos from outer space, and that's like the culmination of an idea that was first proposed about 50 years ago. So very exciting for us.
Very cool, very cool. And this and so IceCUBE is a detector in the Antarctic. Can you tell us a little bit about its construction, what it looks like, what it is?
Yeah, so these neutrinos we think are probably the most abundant particles in the universe, but they very rarely interact, and so in order to capture them, you need a very large detector. Mm-hmm. And so even when the first paper was written proposing this idea in 1960, they said you need a detector that's about 1 kilometer by 1 kilometer by 1 kilometer. Wow. And so what that meant was it had to be something that was naturally occurring, because if you actually had to buy and purify something of that size, it would be prohibitive. Mm-hmm. And so they proposed putting and you need a transparent medium. And so they proposed putting it in a deep lake or the ocean or sea. And it was in the late 1980s where Francis Halsen at UW-Madison was attending a meeting and heard an idea of a different way to detect neutrinos using the ice, and that got him thinking about maybe you could use ice as the medium rather than water. And so the first detector put down on the ice was just a single tube, just to see if there were any flashes of light from particles going through the ice. And then we eventually built a prototype detector over a course of about 4 or 5 years. That was finished in the late 1990s, and then from 2004 to 2010 built the IceCUBE detector, which is a full cubic kilometer of ice that's been instrumented.
So as a radio astronomer, I'm jealous because we're talking about a square kilometer array being made in the next few decades. You guys are well ahead of that with the cubic kilometer of, of collecting space. Hang on, I'm trying to screen share a little animation. Hopefully you guys can see this. This is an animation of a neutrino passing through the detector. And that's the Eiffel Tower to scale?
Yes.
Right there. So that's quite impressive. What goes into building something that huge?
So tremendous amount of engineering and technology, right? And so even though there was quite a bit of experience drilling holes with the prototype detector Amanda, this was a whole different scale in the sense that eventually we had to get to where we could drill about 20 holes in one season. And the challenge that we have is we can only work for about 3 months. And that includes setting everything up and then working and then putting everything back to bed. And so we are not able to set things up and then just work continuously. The key temperature is about 45 below Fahrenheit. And it turns out people will still work outside, but the machines don't.
Okay.
And so about the end of October, beginning of November, it gets warmer than 45 below, and then it stays that warm until about mid-February.
Wow.
And so we designed a hot water drill. It's relatively powerful, about 5 megawatts, and that enabled us to drill a hole in about 30 hours.
Wow.
And we eventually did get to where we did 19 holes in one season.
Wow.
But the first season we did 1, so it was not at all obvious that this was going to go.
You have to learn the first time. I mean.
That's right. And so one of the sayings that the drillers, we had a dedicated team of drillers, that they say is that we made the impossible look easy.
Wow. So Megan, working with something like neutrinos or neutrino detector, this is not, when you say, oh, we do astronomy, astrophysics, people think visual telescope. They think, looking at the stars. This is a completely different type of astronomy and science that people are not used to. What are some ways that you get across these concepts of these bizarre particles people aren't used to dealing with to the public?
That's a great question. We like to kind of frame this as a new view of the universe, and so we kind of start with things that are concrete and people can grasp. Things like medical imaging and how advances in medical technology have allowed us to see different things just within our bodies. And kind of applying those concrete examples to something a little bit more abstract is kind of where we start. But actually being based at the South Pole is a really good hook for getting people interested.
Yeah.
So people are interested in exploration, and we're exploring kind of in the extremes in the universe and within our world. Just being at the South Pole is kind of extreme exploration in itself.
Yeah, absolutely. Do you find that people have heard of neutrinos in general? Are they at all familiar? Or is this really new for most people?
It kind of depends on their background. So it's becoming a little more common, and I think that is in part due to neutrinos going faster than the speed of light, and that whole debate that happened with the opera experiment. And so some great media coverage over scientific uncertainties have really helped bring this kind of more into the general public's mind.
Yeah, interesting.
So you talked about drilling through the ice and the different seasons that you had to do this with, and I love hands-on activities. So you guys actually have an ice drilling activity. Can you tell us a little bit about this?
Sure. So we replicate, on a much smaller scale, we replicate the drilling process done in Antarctica by bringing in anywhere from a 10-pound block of ice to a 300-pound block of ice. And also, I can see you're showing the in-classroom or at-home activity as well. You can do this just with freezing a milk jug of water. And then just taking hot water, and you need a little bit of pressure. So we use pipettes or squirt bottles, and you can replicate the process that we used to drill 2,450 meters into the ice, but just at home.
Yep, we're going to have to do this on a future week when we do hands-on demos again. That looks super cool. That looks super cool.
It's very fun, and there's lots of pictures on our Facebook page and on our website as well of people of all ages participating in ice drilling.
And did you create that activity, Megan, or do you have a group of people that you're working with to sort of develop these things that help teach all this?
So that activity was kind of in place before I started here. And we do work with a group of teachers through the Upward Bound program. So every summer we have a group of about 40 to 60 students that come and get math and science curriculum at UW River Falls. And that's always based on IceCUBE science. But they use what's called a narrative arc to introduce, kind of like we said, concrete topics, and then go to more abstract, like neutrino astrophysics. And so some of the activities we have on our site were developed with teachers working with the Upward Bound student.
Okay. And that's more of a high school level student then, right? Is that what you target your activities for, or are they broader range?
Through Upward Bound, they're targeted at a high school range, but we do have activities that we kind of scale to all different audiences. So we have an LED programming activity, and that's been done by kids, 3 or 4. They just need a little more guidance. Oh. But we're really finding that young kids are really
young.
New technologies, and they're really using it.
We were just talking about that at lunch. We had a staff lunch today. We were talking about 6-year-olds teaching us to use our own devices. So that's fantastic. That does not surprise me. And then you have high school interns as well. Can you tell us a little bit about that internship program?
Sure. So our internship program over the last year and a half has grown from just 1 student to about 26 students. And they meet once a week for a couple hours, 2 hours, and they meet with graduate students, postdocs, and some of the faculty members. And they start off with a quick introduction to a new topic, and they get about 5 slides on the new topic, and then they break into groups and discuss, kind of brainstorm questions, find out what else they would like to know about the topic, and then come back together and kind of learn together about the topic and really drive the presentation from their own questions. And then in the second hour, they work on a project on their own. So we have some programming-based projects where they sort through data from the detector, some more engineering and electronics topics where they work on controlling different devices, and we have some more expanded lectures, and then actually a cell phone cosmic ray detector that is going to be an app hopefully soon.
Ooh, I like that.
Yeah, I'm going to try that.
So this is for students who are in the area near the university, I take it, right?
Yeah, these are students near the University of Wisconsin-Madison. So we have students from Janesville, Madison, Waunakee, but it's a pretty small group at this point.
Cool, cool.
Do they apply to get into that program, or how do you recruit them?
Yeah, so we have an application process. We were initially going new interns every school semester, but it looks like this group of interns is super interested and really engaged, and so they're going to stay on for the year. So they apply and need a teacher recommendation, and it's a pretty simple, painless process. They write a statement about themselves and provide a teacher to write them a recommendation.
Wow, it's a great experience, yeah.
And then you're also doing local events as well. Can you tell us a little bit about local events in Wisconsin relating to IceCUBE?
Sure. So through the Wisconsin Idea Endowment through the UW system, we have a Riley Baldwin grant. And so with that, we're traveling to every 2- and 4-year UW, so University of Wisconsin system school. So there's actually 26 schools in the UW system. And so we do an event at each campus and in each community. And the events range from kind of traditional lectures to science cafes, where they're really more driven by the audience, hands-on activities, classroom visits, and we're also kind of trying to introduce our new planetarium show at communities around Wisconsin.
Yeah, can you tell us a little bit about that, the new Full Dome show?
Sure. So if Jim wants to talk about it a little bit too, he's actually the co-director on it.
Very cool.
And we both worked on the writing and kind of direction of it, but I'll let him speak to that a little bit.
Yeah, so we worked with the Milwaukee Public Museum to make this Full Dome video show. It's a 30-minute show that basically starts, from an introduction to a very quick, what were ancients looking at the night sky, to how do we get to this new type of astronomy. And one of the neatest things, I think, is we did animations where you actually fly through the detector, 2,000 meters below the surface of the ice.
Wow.
And watch the particles come by. And so there's simulations, of the kind of explosions we think are going to produce these high-energy neutrinos, and then interviews with scientists who are working on the projects. And then the other really neat thing is we sent a cinematographic quality camera down to the South Pole, and so we have footage from the pole in the film as well. So we had our premiere November 21st, and that's available for a nominal cost for distribution. We have a flat screen versions as well, but it really comes live in the dome environment.
So do you really get an experience of what it's like being down there from the footage, do you think, in the movie?
Yeah, it's surprising how three-dimensional that really looks. And so when you're in there, and the modules that detect the light, we call digital optical modules, or DOMs, really look like they're suspended in the theater, and there's a part where you go up and you get a close-up view, and then it opens up and shows you the electronics inside, and so it really feels like you're right there looking at it.
That's so cool. That's so cool. Yeah, we are involved in a planetarium. So words. We did a Full Dome planetarium show about colliding galaxies. We talked to the directors of that and how to build a planetarium show from scratch from a bunch of scientists, and the rendering and all the work that goes into that. So congratulations on the premiere. That is a huge project and very cool. And then you guys also, I think, James, you've been involved in taking teachers to the site as well. I would love to hear about this program, and I think our educators would love to hear about how you can get involved in something like that.
Yeah, it's a great program. We've been involved with this since I became a member of the predecessor project, which was called Amanda. So before, the first project was called Teachers Experiencing Antarctica and the Arctic, and we had 3 teachers go and work with us with that program, and now it's called Polar Trek. And it's the same basic principle. They pair teachers with researchers in the Arctic or the Antarctic. And they actually become part of the research team, and they deploy. And depending on the particular project they're working on, they might be gone from 3 to 6 weeks. And so, and what we've done is try to keep those teachers that we've worked with part of our team. And so, for example, the teacher that went in 2001, Eric Moose, we still work with him almost every year with the Upward Bound program. And then the teacher that went to a few, I think 3 years ago now, Katie Sheary, also has stayed involved quite a bit. So she's been back to River Falls, I think, 4 years working on that Upward Bound program. So they get a chance to really become part of that team. I think one of the things that surprises them is for our project, we really don't do any science per se when we're at the South Pole. Mm-hmm. We're building stuff, right? Mm-hmm. And so they go down there and they shovel snow and they carry boxes, and, right? You know, and it's when you think of science, you think of these, you know, very abstract and, you know, high-level thinking, but actually it takes you know, real human power to construct this, and that's really what's going on at the South Pole in our project, right? So we had 50 to 60 people down on the ice directly working on our projects in addition to support people. So during that construction period, we really had about a third of the people that were on the ice were working for the IceCUBE project. You know.
What kind of qualifications do teachers need to get involved in such a program?
So there is a if you just Google Polar Trek, and it's Polar and then TREK, you'll get to their web page, and the time frame is such that we just now have picked the teacher that will go for the following season. So the 2014-2015 season. So they should start thinking about this now, because the application takes some time to fill out, because, you know, we have a lot of people who are interested in this, and we need to get as much information as we can get to get an idea of what this person can contribute. So mostly what we look for is someone who's going to be a good team player, because the resources are such that they have to contribute, right? So they're not there just standing along the sidelines, you know, taking pictures. They're actually part of that team. And so so that's one of the things that we try to glean from that information that they provide is, you know, how do they react in an environment where maybe on a daily basis they have to do something different than what we had planned, right?
Yeah.
And then the next thing is what can they contribute? Yeah. and then what can they contribute to bring that experience to a greater audience, right? So it's a rare experience. It's you know, relatively expensive to send someone down, so we want that to get communicated to as broad an audience as possible. So.
Wow. What kind of lessons do they come back with to their classes?
So you know, they span quite a range. One of the ones that we've used occasionally is to simulate adaptations to cold. It turns out if you take like a baggie and then fill it with Crisco, you know, that layer of fat really gives you tremendous insulating properties. You know, I think you've done that one, haven't you, Megan?
Yeah, so it kind of simulates the fat that animals, Antarctic animals have, and the cold weather gear that they wear at the South Pole kind of gives an extra layer of protection, and so you can use these baggies with Crisco on either side, and then have them put their hand in ice water and see if they can either like how long they can keep their hand in the water versus if they don't have that extra layer of fat.
Okay, I'm totally imagining myself lining the inside of my jacket with Crisco baggies the next time, because it's really cold for public night right now.
Yeah.
That could work.
Don't give me these ideas. Oh my gosh. Okay, I'm going to pause for a quick station identification. You are watching Learning Space with CosmoQuest. We are talking to Jim Madsen and Megan Madsen about IceCUBE. They both work at out of Wisconsin, which is running this neutrino project at the South Pole in Antarctica, and talking about some of the education and outreach opportunities that revolve around this amazing, massive project. So if you guys have any questions, you can comment on YouTube on the event page, and or using the Q&A app. I'm seeing a bunch of hellos and highs and wow. So that's really, really good stuff. So you guys can keep posting and post questions as well. Oh, okay. So I wanted to talk a little bit about. So we talked about ways people can get involved physically. So there's the out of Wisconsin, which there's the Upward Bound program. There's the Wisconsin outreach specifically, but also and there's the new planetarium show that's come out. But you guys are also doing some webcasts as well with the scientists as they're working at the South Pole Station. So maybe you can tell us a little bit about that as well, as we're on a webcast.
Yes. Megan, do you want to say a few words about that?
Yeah, I just want to quick check on what dates we have. So starting in January, we will be offering a few connections with the South Pole. So there are researchers and technicians that are there for the summer construction period, and it looks like we have webcast scheduled for January 15th, which is a Wednesday, and January 23rd. We do not have times yet because we're dependent on the South Pole satellite, and that doesn't get projected kind of quite this far in advance. But we will be posting information on how to connect on our website. So if you go to icecube.wis.edu, there's a section called Education and Outreach, and within that there's a tab called Webcasts. And you can sign up, either classrooms or community centers or just individuals can sign up, and we do kind of a quick overview of the project, and then we allow for each group or each individual to ask a couple questions over the hour. It is always an adventure because we never know when the satellite connection will cut out, but we do have lots of researchers and people with experience working at the pole available locally to answer questions when that does happen.
Cool. Can you share that link to me in the private chat, and I'll share that out on our comment streams for people to look at? So I'm sharing comments. YouTube is allowing links and comments now, so I'm sharing on YouTube and on the event page. If you're watching either of those, you can check that out. So that sounds really awesome. But you guys are also involved in coming up right this week, Friday, you guys are involved in a webcast as well. If you'd like to say a few words about that.
Yeah, so we can't say too much because this is embargoed by the organizer of the event, but it's a nice award, and there'll be an international webcast that will connect people from the site that's involved with this designation. I have to speak kind of vaguely here, but it'll be across Europe as well. Many of our European collaborators will be on this webcast, and it's a nice recognition. Let me put it that way.
Okay, so we will share that when you can share it on Friday. We'll share that link. Yeah. So yes, okay, grabbing the link. Sorry, I'm like sharing links and talking at the same time. It's always good times. We got a question From Jim Meeker, asking how often do you get a detection with IceCUBE? What are the projected detection rates?
Yeah, so I think it will surprise you to hear we actually see about 100 billion particles a year.
Wow.
And so that's about 3,000 a second. Those are almost all not neutrinos.
Noise, yeah.
Okay, so those are cosmic rays. When they hit the Earth's atmosphere, they can produce a particle called a muon that's actually able to make it down into the ice and creates light. And so about 3,000 times a second, we see one of those. 1 out of a million of those, or about 100,000, are neutrinos, okay, of those events. So 100,000, so that works out to a few hundred a day of neutrinos.
Okay.
The problem is those neutrinos were overwhelmingly created from the cosmic ray shower. So they're interesting, but not what we're really shooting for, which was a neutrino that was created in a big explosion in outer space. So there's somewhere on the order of 10 to 100 neutrinos buried in all those events that came from outer space. And so that was the big breakthrough we had. We are just on the cover of Science magazine November 22nd, and we've identified over 2 years about 28 neutrinos that look like they came from, most of which look like they came from outer space based on their energy.
Are they coming from supernovae or something else?
Well, it turns out supernova are not, they produce a very large pulse of neutrinos, but they aren't real high energy.
Okay.
And so the energies that we're looking at, if you have a chemical reaction and you assign an energy value of 1 to that, then nuclear reactions take about 1 million times more energy. Okay. Those are roughly the energies scales of the neutrinos produced in the sun, and also, it turns out, neutrinos produced in supernovas. We're looking for neutrinos that have 1 million times more energy than those. So 1 trillion times, and actually the ones that we detected are 10 to 100 to 1,000 trillion times more than a chemical reaction. Yeah. So they're the highest energy neutrinos that have ever been detected.
So what kind of processes are creating these super high energy neutrinos?
Well, that's kind of the...
Is that the question?
That's the whole question, right? And
yeah.
So the types of things that we think are good candidates are, there are these tremendous explosions called gamma ray bursts, and they occur relatively frequently, like on the order of once to twice a day, somewhere in the universe. There's a giant explosion that lasts sometimes less than a few seconds, sometimes only milliseconds, but produces more gamma rays than the whole rest of the universe combined while that's going off. And then they're just gone. And so we know that they're producing high energy light. We think that they're probably going to produce high energy neutrinos. Another possibility is around a black hole. So there are sites called active galactic nuclei, and they're also tremendous cosmic engines. And so you need to have protons, it turns out. Anytime you have protons that knock into something, ultimately neutrinos come out. And so you need a high energy source, powerful engine, and then you need to have neutrons. It's possible for, or excuse me, neutrons or protons. It's possible, for example, that gamma ray burst could be mostly electronic phenomena involving electrons, in which case it wouldn't produce these high energy neutrinos. And so that's one of the questions we're hoping to contribute to, is what is that process for these gamma ray bursts.
So Richard Drum, our podcast producer, hi Richard, says you're not just waiting for a type 2 supernova, you need a hypernova. So that is something that could create a gamma ray burst in the distant universe.
Exactly, yeah.
Super, super, super massive star exploding there.
Yep.
What about neutron? You said protons and neutrons. That just made me think. What about neutron star collisions?
Yep, that could do it too.
Okay.
Yeah, yeah. So, yeah, so you need something that's, what we know is that there are very high energy cosmic rays. So I talked about this 1,000 trillions, right? There are cosmic rays that are 1,000,000 times more energy than that even, So like 100 million times more in energy than anything we can produce in the biggest accelerators on Earth. And how they get those energies and where they're getting accelerated out in space is still a complete mystery. So we think the neutrinos are going to help us find the diagnostics, just like when we discussed earlier that by getting the MRI, you're able to find a tumor that might explain some symptoms. We think the neutrinos are going to help us identify sites and mechanisms for some of these mysteries that, we know that they're there, we just don't know how they're getting these very high energies.
So we also have a question from Tom Nath. How do you filter out all of these neutrino events and identify which is which? What's the signal from the noise?
Yeah, so a lot of people think that the biggest challenge was working down at the South Pole. And there was, as I mentioned, some technological challenges there. But within the science community, there was some skepticism, depending on who you talk to, maybe a lot of skepticism that we would never find the neutrinos, right? So that's really a hard question, because if you think about it, if we made a mistake 1 out of 1 billion times, we would not see the neutrinos, right? And so what you have to do is you have to have a detector that's very reliable. You have to have really good archiving technologies, and then you have to have people that are very clever who can write an algorithm that throws out the good stuff and keeps the stuff that you're looking for. And so there's basically kind of 2 ways that you could identify if neutrinos came from outer space instead of coming from an interaction in the Earth's atmosphere. The way we've found them right now is we look for very high energy ones. And above a certain energy, they cannot be produced in a collision from a cosmic ray in the Earth's atmosphere. So that's these 28 events, that's how we've identified that. But the other way we could determine if we had particles from outer space is if we had a cluster of particles from one direction. They basically, the cosmic rays come in to a very good approximation at the same rate from all directions. And so we see those 100,000 equally, distributed. But if we saw some that came from one particular direction in space, or if we saw some that came in conjunction with signals that came from a gamma ray burst, then we'd say, those are associated with that, and they must have been produced in that big explosion or some cataclysmic event. So that's the trick, right? Is finding either a parameter like energy that makes them unique, or some clustering in time or clustering in space.
So then what is it like taking this experience now to the high school level, the high school interns, the students you have working with you? Because something we've talked about a lot on this show is the new science standards and how they're working to make them more like real science. But when you throw real science at a high school student, what is that like, getting them involved in this process with something so detailed and intricate?
Yeah, Megan, do you want to talk maybe about the part where they were looking for multiple particles going through the detector?
Sure. So our interns get a pretty basic overview of coding, and they use Python to sort through the data. And I have some pictures, I can try and show.
Sure.
Yeah.
So this is that working?
It's frozen, which means it's probably working on it. Oh, there it is. Yay. Okay. Now everyone can see it.
So this is one of the representations of data through our detector. And so this is one of the really high energy events. And what you're seeing is where the red starts. That's where the neutrino first interacted. Mm-hmm. And I think you're seeing one that's traveling kind of in a line instead of a ball. Is that correct?
Yes.
Okay. So this is a certain type of neutrino signature, and so that tells our researchers a little bit about what type of neutrino it was when it interacted, and then the intensity, the size of the bubble, tells the energy. And then the color just lets us see the direction in a still image. So the colors of the rainbow show time.
Okay.
So the interns look through data that's actually not been able to be classified by the computers. So the computers, for whatever reason, say that they're going in a different direction than what they really are. And so the interns get to look through real data that really our researchers haven't even looked through. They just kind of throw it into a pile that says it wasn't classified correctly, and then eventually they'll get to look at it. So our interns are actually helping us look through and sort for multiple events going through the detector at once, because that's one thing that really trips up our algorithms. Mm-hmm. So we call those coincident events, when multiple neutrinos or muons are traveling through the detector at the same time. And so that actually is very exciting for our interns to see. They get to work with the real data and see. They work with the actual data and see if they're able to kind of contribute towards the understanding of the algorithms and kind of improve the process that the scientists go through.
Do your interns do any kind of presentation with, putting what they've done or accomplished together at the end of their time and share that out with either the other interns or you guys or the public?
So we're doing that actually next Thursday for the first time. They'll present on their projects, because they in the second hour of the internship they're doing different group projects. So they'll be able to present kind of what they've learned, their findings to each other, and then we're inviting kind of our local researchers here in Madison, and then their high school teachers as well. And then in the past we have let them present and kind of talk about IceCUBE at public events, and so we invite them to come and volunteer and explain the project and explain what they've been working on, kind of at public science events.
Awesome.
And we also had the first intern gave a presentation at our collaboration meeting. So we hold 2 collaboration meetings each year, and it's a fairly big deal, because there'll be somewhere between 150 and 200 scientists attend those meetings. So she really did a great job and talked about how meaningful it was for her, because the things she was doing in school just didn't engage her, and she just really took to it, and it's made a tremendous difference in her schooling. So
that's fantastic.
Yeah,
that's really cool.
Do you get a sense from your other interns of changes like that the program has made with them? I imagine they all come fairly interested in science, but anything else that they seem to discover or learn beyond the projects themselves with the program?
I think they get a really good sense of what it actually means to be a scientist, and that it's not quite as abstract as they thought. So we have a great participation from our researchers and graduate students here, and so they get some like nice one-on-one or just really small group discussion, so they get a realization of what it means to go to school to be with a research background, and kind of what are the applications of this type of education. If some of the students are looking at staying in academics, or if they're looking at going into different industries, kind of just knowing what having a science background and being able to do this type of research allows them to do, after college, after graduate school. I think that's one of the things that is really helpful for the students, because like you said, they're already interested in science, but they might not know what that means after they get a degree.
Yeah.
Right. One of the interesting kind of sort of negative sounding things, but actually turns out to be quite positive, is they also get to see that somebody can be quite proficient at a given task and still not know everything. Right?
Yeah.
And so we find, for example, when we do the webcast, people ask all these questions that have nothing to do with neutrinos, and our scientists down there are going, well, I don't really do that kind of research, right? And so I think people have this stereotype that if you're a scientist, you know everything, right? And they're quite surprised if they ask a question and they go, well, I don't know that, So.
But it's good to be comfortable saying I don't know that.
Exactly.
So kudos to your scientist for doing that.
Well, and I think it's reassuring to the students, to say, oh, it's okay if I don't know everything up front. That's what we're here is to learn, right?
Yeah, that's right. And I wonder if that's something your teachers learn too, because that's also a sort of a hurdle with a lot of teachers, is that they feel like they, as a science teacher especially, like they have to have all the answers. So it's a good thing to become comfortable with, that there's so much more out there and you can't know it all.
Yep. Yeah.
So we have a question that is near and dear to our collective heart at CosmoQuest, since we do so much citizen science. Tom Nath is asking, is any of this data available for crowdsourcing with the public? Do you have any citizen science plans in mind?
Yeah, so we're working on a couple of things, and one of which would ultimately, we hope, get to a citizen science type project. The challenge there is we work so hard to build this detector, right, that the scientists are reluctant to release anything that allows somebody else to discover something that while they still think there's a good chance. So it's a kind of a peculiar thing. You have to find a topic where you go, there's almost no chance, right, and there's enough other things that we probably won't get to that. But maybe if we had enough eyes look at this, we would find something. But it has to be something, as I say, where you have to convince somebody, but really not so much, because if they really thought there was something there, they wouldn't let somebody else do it, right?
Interesting.
They would want to get the exciting things. So, so that's the challenge, right, is how do you find something? Whereas, like, there are some things like looking for supernova, for example. There are so many supernovas, right? And it's been done that they say it would just be great if we found another one, right? And so let's have people come through that. So we're not quite at the point where we've identified what it is we would want people to look for. But there are things, as we say, that could be helpful, where we say we have this, fairly substantial number of events every season that we cannot reconstruct. And so it would be helpful to have people look through and see if they can identify where are they failing, and then maybe that would direct us to a better way to reconstruct those. There are other things, for example, it turns out that there's a particular type of event where you might see two tracks that come through kind of in parallel but separated. And that's a signature of a rare event. and very hard to write a computer program to identify. But we're still not quite at the point where we're going to turn, data that we think might have value, so to speak.
You're not so overwhelmed with data that you have to
It hasn't hit that point yet.
Exactly, yeah.
Our projects are well at that point. There are millions of craters on the moon. And
exactly,
yeah,
right.
There aren't enough grad students.
Exactly.
Yeah,
So
and you have the interns doing this work too, which is a fantastic experience for them.
Yeah, Nicole, I sent you a link too for our data that is public.
Ooh, shiny.
So we have data that has been, reviewed, and findings have been released from the collaboration already. And you can look through all the data already. It's on our website. It's maybe not in a form that many people would be able to look at or do much with. But it does include the data from the 28 high energy events that was
very cool.
Released in November. And so there is a small amount of data available on our website. And then we are working to create a master class, which would allow mainly students, but it's possible that it would be kind of a web-based learning opportunity where general public people could reproduce different analysis for some of our findings. So we're starting that master class. It's kind of in its beta testing phase right now, and they'll be reproducing the analysis that found these high energy extraterrestrial neutrinos.
Excellent, cool. We have a couple other science questions. Richard Drum's asking, can you tell the difference between the three types of neutrino, and is there new science in that at these energies? And also from Michael Jobin asking if there's a special name for these high energy neutrinos.
Yeah. So the first question, yes, there are three flavors of neutrinos, we call it. There's an electron neutrino, there's a tau neutrino, and then there's a muon neutrino. And the muon neutrino is the one that creates a muon, which they can travel kilometers through the ice. And so they create a long track of light, like we showed. The electron neutrino interacts and creates an electron which interacts very readily and doesn't go very far. And so it creates more like a outwardly going spherical ball of light. And then the tau neutrino, it creates a tau. So there's a burst of light that goes out in a sphere. Then the tau particle travels on the orders of hundreds of meters, depending on its energy, and then the tau particle decays again. So if we were lucky enough to see both those interactions inside the detector, we would see two balls of light connected with a track of light. So we call that a double bang experiment or event. And so we can distinguish the flavor in that way. And then in terms of the name, there's no there's some kind of rough categories on where these things could be produced, but in order to keep track of the neutrinos, we actually have named these 28 events after Muppets. So, so the first two were Bert and Ernie.
I'm so happy right now.
So the event that I have showing right now is called BERT, and
Hi, Bert.
the reason I pulled that up is that's the electron neutrino signature. So you can see that burst of light there.
Oh, yeah.
Yeah. So you see the reds in the middle, where the first light was detected, and then you see the
colors. Oh, okay,
coming
that's
out,
time
right?
again. I keep thinking that's energy. That's time. Right. Okay.
Right, yeah. Yep.
Very cool. So that's another bit of outreach right there, is naming them after Muppets. That's brilliant.
Yeah. And so the two highest ones were the first ones that we found. So those were Bert and Ernie. And then they go on from there, and it turns out there's more Muppets than I thought, right? So,
Yeah, really.
And we've actually found one that's the highest energy one that's been detected that's about twice the energy of Bert and Ernie. So that one, any guesses what that one's called?
Animal?
Animal.
No,
Oh.
You gotta think large.
Big Bird.
Big. What's that?
Big Bird.
Big Bird. There you go.
Hey. Okay. I think high energy. I think animal.
I know.
Animal is my spirit animal. I just rewatched the original Muppets movie.
Yes.
Oh,
That's cool. That's really cool. So we're getting to the end of the hour, so I'm going to go off with a few announcements, and then I would like Megan and Jim to end the show telling us a little bit about how you all can keep up with the interesting science and education opportunities involved with IceCUBE. But first, I will do announcements. Our next hangout is Friday. The Weekly Space Hangout is hosted by Fraser Kane and a bunch of us rowdy astronomy journalists talking about the top space news for the week. In fact, I have a special request from one of our Twitter followers, so if you do have a request for a story, we will try and work that in. So that is noon Pacific on Friday, so check CosmoQuest page for that, or Fraser Kane's page. Sunday night is the Virtual Star Party. That's, I think now it's 6 p.m. Pacific. I'll have to double check when I write the newsletter tonight. So you can actually get a telescope view through our amateur astronomer telescopes around the U.S., around the world. Trust me, you want to do it that way. I was just outside last night with our 8-inch telescope for a public event, and it's cold. So join the Virtual Star Party. You can watch from the warmth of your house. Monday is the live astronomy cast recording with Fraser and Pamela. That is also at noon Pacific, and then we come back around to Wednesday. I don't think we have any specials coming up this week. And then Friday, you guys have an event about which it is partly embargoed, so we will share that link as soon as we see that come up. So that'll be cool. So maybe you guys can finish off by telling us a little bit about how people can keep up with the IceCUBE project and find out more about these education and outreach opportunities.
I'll say a couple of things, then turn it over to Megan. So we try to find ways that people can participate on multiple levels. And so there are social media feeds that Megan can talk more about. On our web page, we list all the papers, so the people who are super engaged can actually go in and get copies of all the publications.
Very cool.
We have
open science.
Yeah, good luck with that.
Yeah.
But, so then kind of the next level down for the person who's interested but not an expert, we've been doing like 1 to 2 page summaries of those papers that are geared at that audience. And so those are posted on our webpage as well. And then the other thing I hope that people will do is to follow the blogs and postings from the teachers that are deploying at the South Pole. And so if you go to the Polar Trek webpage and just do Polar Trek and IceCUBE, it'll come up. Obed Fulcar, teacher from New York City, is scheduled to go. I think the 10th, roughly the 10th to the 24th is on ice dates. So I'll let Megan add any other ideas.
Sure. So I did post the link again for the Polar Trek expedition. So if you want to forward that on, that would be great.
Yep.
We also have weekly updates from the pole. They're mostly picture-based, maybe a couple sentences about what's going on at the South Pole, and kind of from the perspective of the IceCUBE team. We do have winter rovers that are there for 13 months, so there's always someone there to talk to. There's always someone there making sure a detector is up and running. We do have outreach based site or pages on both the icecube.wisc.edu site and the WIPAC, WIPAC.wisc.edu sites. And that's where we post most of our content for informal learning, formal learning, and you can always email us at learn@wipac.wisc.edu and let us know about events or ideas you have, and we're always happy to partner with people.
That's awesome. Thank you guys so much. I learned so much today. That was really fun.
Yeah, me too.
I've been sharing all the links that Megan has been sending me on the YouTube page for this, so they're all in the comments. And on the event page on Google Plus as well. You also included a link about naming because now we're getting questions asking about Snuffleupagus and Cookie Monster. So go check that out.
You know all the names now.
You just made everyone so happy. All
Yes,
right.
there is a Snuffleupagus.
Okay, there you go. That's another big one. All right. Thank you so much for joining us. And thank you, everyone, for your comments and questions. And we will see you next week on Learning Space.
All right.
All right.
Thanks, everybody.
Thank you.
Thanks.
Bye-bye.
Okay. We're almost all unmuted. We're
Hi.
back. Awesome. Okay, hi everyone, and welcome to this week's Learning Space. I am your postdoc with the postdoc, Nicole Gugliucci with CosmoQuest. I am joined by my very awesome co-host down at the end of the screen.
At the end,
Georgia Bracey. Those of you who have been watching, we are still in the middle of our office move.
Yay, boxes.
The boxes in the background, and Georgia's been kicked out of her own office. So, but we're still here. We're still going. So thanks for joining us. Feel free to share the link, to comment on YouTube, on the event page, or using the Q&A app for Hangouts. And we will be watching for your questions and comments, so say hello, ask questions, all the usual stuff. And I am joined today by James Madsen and Megan Madsen, both of whom work with IceCUBE, which is a searching for cosmic neutrinos from the Antarctic. And we asked them to come on to talk some about IceCUBE and the neutrinos, but also a lot about the education and outreach programs that go along with this project. And I'm really excited. I know very, very little particle astrophysics beyond what I learned in my high energy astrophysics class in grad school, so I'm really excited to learn some new stuff. So thank you both for joining us.
Thank you. Yeah, we're looking forward to it.
Awesome. So, Jim, do you want to maybe start us off, just broad overview of IceCUBE for any of our listeners who haven't heard of it or aren't up on their neutrino astrophysics?
Sure.